This is the tutorial for the Chapter 3 problem solving connections found on pages 131 and 132. So let's take a look at what we'll end up having to deal with. So on this first problem, what we see is they'll give us a series of continents and populations, and I only have two here, due to this just being an example of what you're supposed to do. And it asks us to first write the populations of each continent using the same power of 10, because they'll eventually want us to add these together. So we're going to take the 1.0 times 10 to the third, and I'm going to change this to a power of 10. So if I do that, what I need to do is I need to add on some more 10s here. So basically multiplying by a power of 10. So it's the same as this power right here, 9, because that is the largest power of all the continents. And so we'll go ahead and we need to add on 6 more 10s. And so basically it's like multiplying by 10 to the 6th power. And what that means is I need to make this one smaller. So again, I'm making this one bigger by 10. By 6 10s, and so what I need to do is make this one smaller by 6 10s. And so when I do that, that means I need to move the decimal over 6 spaces. So once I move it over 1 space, 6 more spaces would be 5 zeros having to be added. So I'm going to have 1, 2, 3, 4, 5, and then the 1 times 10 to the 9th power, and that would be the population with the same power for Antarctica. So you'll do that with the rest of them, and then the next part, it tells us to add multipliers for each population. Well, the multipliers are these numbers that we are changing the decimal location of. So we take all these numbers and we add them all up. So for instance, if I was to add the 2 times 10 to the 9th, and I have the 0.00000, so 5 zeros, and the 1 times 10 to the 9th. When I add these numbers up, I'm adding up the multipliers, but you just got to line up those decimals very closely. And so notice that I've got 5 zeros, so 1, 2, 3, 4, 5, and then the 1, so that means I have to make sure, again, the decimals are lined up, and I'll have 6 zeros on top. So when I add this together, I get 2 point, and then the 5 zeros, and then the 1, and then we're using that same power of 10 again as we came up with in the part A. And so that's the way you do it with all the numbers. You're going to add all the multipliers together. Next part is to write the world population in scientific notation and standard form. So basically you're just taking your number that you got when you added up all these multipliers, and for instance mine would just be this because I'm only dealing with the 2 continents, but on your example you'll have to deal with all 7. And so I've got it in scientific notation, and then you take that answer and you put it in standard form. So standard form says I need to move the decimal 9 spaces to the right to make it bigger. So 9 spaces, I'd have to move it 1. This is 6 values here, so I've got to rewrite those. So I got those 5 zeros, and then the 1, and that's 6 values, so I have 3 more spaces to go, so I'd have to add on a few more zeros, 3 more to be exact. So I've got the scientific notation in standard form, and then they want us to do is to find the population, or write this number in scientific notation in standard form, and this is going to represent the approximate population of the people who could live on the moon. I did change this number so it wouldn't be the same as the problem that you'll end up having. But what I would end up doing is, if we go ahead and pull up a calculator here, I can take that number, the 1 times 10 to the 8th, so I can do 10, and then to the 8th power, or 18th power, and that gives me this number, but then I have to take its square root. So I have to do the square root of that, and let's see here, this looks like the button that I need, and let's press equals, and they give me this value. And actually, let's see here, that number, don't see the E in there, so let's go ahead and take a look at what we've got. So from this point, taking a look at the calculator again, we'll go ahead and try this once more. I pressed the wrong button there. Here's my square root button on my calculator, so we'll try that once more. So I have 10 to the 18th power. I got this large number, and then I'm going to take its square root, and so this is my value that I end up coming up with. So it looks like I count those spaces, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros there, so I'm dealing with 1 billion. So I'll go ahead and write those zeros, and there's 3, 6, 9. So again, your number is going to be just a little bit bigger because you have a different exponent on the power of 10. So what we want to do next is look at comparing the total population on Earth to the number of people that can live on the moon. And so what we have is, we see that in my case, again, in your case it will be a little bit different, I could say something to this effect: 1 times 10 to the 9th. So again, it's just a little easier using that scientific notation because it takes up less space. But that represents 1 billion people can live on the moon. But, and in my case, there are 2 million. Actually, I'll use the exact number I had. I have the 5 zeros and the 1 times 10 to the 9th people on Earth. Again, your number will be a little bit different because you're going to add in all the continents. And so what I could say is, which is twice, or about twice, as many people. And so again, the way I show that is, if you just take the 2 million, your number there, and you divide it by the number of people on the moon, where it shows 1 times 10 to the 9th, the 10 to the 9th will cancel out. 1 goes into 2 about 2 times. So again, that's how I'm getting twice as many. And so, which is about twice as many people. And so, only half the Earth's population could live on the moon. So that goes over that question. Let's take a look at the other problems. And when we look at those, it talks about, on page 132 and 133, can the population of each continent live on the moon? So they're going to compare these things. So we're looking at different ways to compare numbers, whether we subtract or divide. And we'll see that in this example. And so the first part says, use subtraction. So we're going to use subtraction in scientific notation form to compare the continents and whether they could live on the moon. So our example is Africa again, and we're comparing it with this number, and we know that when we go ahead and do the subtraction, if I went ahead and subtracted the number of people on the moon, which we know, again, this number is going to be 1 billion people, we end up subtracting these, and we end up with a negative number if I subtract the number of people from Africa. And so what that negative number represents is that those are the people that would not fit on the moon. So this means 1 billion people would be left off the moon from Africa. And again, you're going to end up using all the different continents and find out which one would be able to fit there and which one would not. And then we're supposed to compare using division and in scientific notation to compare. And so when I do that, and they want to compare the population of the continents to the population of the moon. So the way I'm going to set that up is this. I'm going to have 2 times 10 to the 9th power, and I'm going to compare it to the population on the moon. So that'd be 1 times 10 to the 9th. And what I get is 2. And so what that represents is there are twice as many people in Africa than could live on the moon. And again, you'll do that for each of the different continents. And the last question says, compare the population density. So the density is how many people can fit in a certain square, certain area. And so it talks about, example, if the moon's surface area is this, and they give us the surface area, and the possible population is this number, find its density. And so when we're trying to find density, density is people per kilometer squared in this case. So it's people per area. So we're doing this. We're doing the 1 times 10 to the 18th and taking its square root. And we're dividing by 3.793 times 10 to the 7th. Now, you'll definitely need a calculator when you do that division, because when we do this, again, I'll put in that scientific notation form, we end up with a decimal, and it's going to be quite large, and so I'm going to just round it off a little bit. And so what I got was about, and then I have this 0.264 times 10 to the second people, and so it's not quite in the scientific notation form, so I'm going to rewrite that as, and I can write that 2.64 times 10 to the first people per kilometers squared. And so now I just need to compare it to Boston. So you compare, again, using either the subtraction or the division. I'm going to choose to use the division. So up to the side here, I'll go ahead and take a look at those comparisons. So the population of Boston is 5,000 people per kilometer squared. The population of the moon would be 264. Or actually, I'm sorry, 26.4 if I just move that decimal one space over to change this to standard form. And I go ahead and do that division, I end up with about 189. And so what that means is 189 times as populated or as dense as the moon would be as dense. And so we just state something about that. So we say Boston's population density is 189 times greater than the population on the moon, or what the possible population on the moon would end up being. But we could say something about, however, Boston is a large city, and the rest of the Earth has a lower population density. So these are examples of what you're going to end up doing, and good luck on that assignment.